Okay, well now we're going to talk about sketching gradient vector fields. And I think sketching gradient vector fields is a lot easier because you can make use of the level curves. So what am I talking about by a gradient vector field? I mean something that looks like this, gradient f. And it's the vector of partial derivatives of f, if I'm in 2D, for example. And because I am lazy, I will use f sub x and f sub y. And also, really, these should be angle brackets, but I mean, I think in practice, people often just use curly brackets too. I mean, it's not right. You should use these, but I certainly won't care if you use curly brackets by mistake. So let's do an example of a gradient vector field to show you what I mean. So if we do probably my favorite function, which is just x squared plus y squared, then the gradient is going to be given by 1 over the square root of x squared plus y squared. By the chain rule, we also have 2x, so overall we just get x over the square root. And if we do partial derivative from y, we get something that looks very similar, but we're differentiating y, so we need a 2y. That's the derivative of that inside portion. So we just get y over that square root. So we get the gradient of f is equal to x over the square root, y over the square root. And really, if you want to understand what this is really just r divided by its length. So I would say it's the unit r vector. So this, I mean, this is actually a pretty straightforward thing to draw because it's pointing it has length 1. So now you just point these arrows at all point in the same direction of the xy. But so you could just directly draw. But an easier, well, for this, I don't know if it's easier, but another way is to use the level curves. Use f equals c. So that means r equals c is a level curve, constant radius. So I could draw just a circle, c1. So for example, c equals 1. And then we could also draw c equals 2. And from this, I know the gradient is normal to the curve. So by normal, I really just mean perpendicular to the tangent vectors. So, and it also points in the increasing direction. Increasing direction. So our function is f equals r, so f increases with r. So it points out. Okay, so I could just draw arrows perpendicular to that circle, and that's actually legit. And I'm always drawing the vectors out because f increases with r, and the gradient points in increasing directions. Okay? I mean, that really is what's going on over here as well. But notice how we just took a bunch of points and it's not really clear what's going on. I think this picture, where we have level curves, is a lot more transparent. Okay? I think this is a pretty useful trick. Let's talk about another example of this. Okay. So if we do f of x, y equals 1/2 x squared plus y squared, my second favorite function, then the partial derivative is just x and y, depending on which one we differentiate. So how to draw the vector field? Well, I will just use the level curves. Okay, so f equals c that really means r squared equals c. So again, constant radius is our level curve. So I'll just draw a couple of these constant radiuses, radii, and so c equals 1, for example, c equals 2, c equals 3, not to scale, of course. Then to get a feel for what the length is, well, the length of that gradient, it's really just the square root of x squared plus y squared, so it's r, right? So the length increases with r. So I could draw a very small arrow perpendicular to that circle. Then I'll draw a slightly bigger arrow on the second and bigger radius. And now I might draw a really big arrow, not to scale, of course, but just to indicate what is going on. Okay, so that is a qualitatively good picture of what that vector field looks like. Okay. Now, what about in 3D? Can we do something similar? Also a favorite function of mine. It just has that extra z squared. So, as you can imagine, the partial derivatives will look very similar. It'll just look like x divided by that square root. And I hope you'll forgive me if I don't write that square root out over and over again. Well, I could try a bunch of points and just see where the directions are. Or what I could do is I could just look at the level curves. So f equals c. This is just our rho equals c. So now rho is, of course, the sphere radius. I also know that f equals rho increases with rho. So that means the gradient f length increases with rho. Oh, no, I'm sorry. What I meant to say was the direction. So that means gradient f points in the radial direction, so it points out. Okay, so I will attempt to draw a sphere. The success of this might be debatable, but hopefully it gives you a sense of what is going on. Okay, so I'm just going to draw a few arrows. This will be a small arrow. Oh, actually, let me just check the length here. So really what's going on is the gradient is, well, it's x, y, z divided by that square root, right? So it's just r divided by r, or rho, or however you like. And so it has length 1. Yeah, I guess you have to check that length after you do the gradients. So that's why this is useful. So this is for the length of the gradient vector. So I'll just draw length 1 vectors on the outer sphere as well, not to scale. And so that's a kind of heuristic picture of what that vector field looks like. Okay, so let's move on to something that's not just x. All right, let's try f of x, y equals 1/2 x minus y squared. So again, I'm just going to look at the level curves at first, so that'll show me what's going on. So f equals c implies 1/2 x minus y squared. You can look at these level curves. Really, I think it's fair to call this c squared, because there is no solution if c is negative, right? Because this thing is positive. So let's just call that c squared. And you know what? It's just a constant, so let's divide that by 2. So the solutions of that, really the level curves, are just x minus y equals c. Hopefully this wasn't too confusing. I just took some constant and I called it another constant. Another more convenient arbitrary constant. Right? So these are the level curves. And so in other words, these are y equals x minus c. So if we just plot the level curves, then we'll have a good idea of what's going on. So here's y equals x. And here's y equals x minus 1. Here's y equals x plus 1. And x plus 2, x minus 2. So really this is just c equals... yeah, okay, let's call this c equals 2, c equals 1, c equals 0, c equals negative 1, c equals negative 2. What I did is I changed the sign of the c, but again, our c is just for convenience. So let's not quibble over which c we're using. So now that we have our c's, let's note that the gradient points in increasing f direction. Okay, so c equals 0. In fact, it'll be the smallest, right? Because x minus y will then be equal to 0. So f will be equal to 0. That's the minimum value. So in fact, the gradient will be equal to 0. So I'm not going to draw anything on this line. So c equals 1. You can see f is actually bigger, right? Because f is now equal to 1/2 c squared. So it is 1/2. So it's bigger than what it was at 0. So you can see that moving from c equals 0 to c equals 1, that actually increased. I'm going to draw that arrow pointing perpendicularly to c equals 1, and I'm going to draw it pointing outwards. But actually, c equals negative 1 does the same thing. So c equals negative 1, we again get f equals 1/2 negative 1 squared. So it's again 1/2, and that's bigger than what we started with. So actually going in this direction increases f2. So the gradient actually will look like this. And we can continue to draw. To actually see what the lengths look like, I could say that fx equals x minus y. Fy will then equal to the negative of that by the chain rule. So actually the length increases with c, right? Because this is c and this is negative c. So I can draw a really big arrow for c equals 2 just to get an idea of what's going on, and similarly with negative 2, pointing in that right direction. Okay? So notice that f is because it's actually a parabola. So you don't have to do this, but this is just showing what f looks like. It's a parabola in this. It's kind of a rotated parabola. Okay? And so the vector field will just look like this. Okay? So I think the level curves help a lot with clarifying what's going on. Let's do one more example, because this one's kind of fun. If we look at f equals xi minus yj, as in my previous video, well, this thing is actually related to the angle. Theta equals arctangent of y over x. Okay, so, and why is arctangent? Remember, if we draw the circle, there's this triangle, right, associated with theta, and the vertical is y, this is x, so that means tangent theta is y over x. So what we do is I'm going to take theta x, partial derivative. By the arctangent derivative rule, it's 1 over 1 plus x squared, so 1 over 1 plus y divided by x squared times the partial derivative in x, so it's minus y over x squared. And then theta y is the same thing, times 1 over x, partial derivative of y. So that means if you distribute that x squared inside the denominator, then you end up getting minus y divided by x squared plus y squared. And if you distribute this x squared inside similarly, and I'm going to put an x on top and an x on the bottom, then we get something very similar. We get x divided by that squared. So really, f is actually, it's the square root of x squared plus y squared times minus gradient theta. Okay, so the level curves of gradient theta, of theta, they are constant angle. So this gives me the directions. Okay, so I'm going to now draw constant angles. Constant angles, which way does it point? So if theta increases, then minus theta decreases. So that means theta increases counterclockwise. So minus theta decreases counterclockwise. So that means theta minus theta increases clockwise. Okay, so if we look at the clockwise direction, that shows us where our vector field will point. And so notice how we didn't have to test any x equals 0, y equals 0 values like in my previous video. I am just using the level curves of that gradient. And what that r does, the r in the front, this thing just changes the length. And in fact, we know that the good length of this vector field is 1. I'm sorry, not the gradient. The length of f equals 1. So that's why I'm drawing my vector arrows like this. And I will also draw a streamline because I think that also clarifies what's going on here. It just shows that particles will move in a circle if they're subjected to this vector field. Okay, thanks for watching.